All right, hey guys, it's Miss Summers with your notes today on volcanoes, day 2. So just a quick reminder of what we did yesterday, or if you weren't here, this is what we talked about. We talked about the types of volcanic eruptions, where they happen, and what kinds of volcanoes they make. All right, so there's two main types of eruptions and then an exception. Our first type are the rift eruptions, and remember, rifts happen at divergent boundaries. Rift eruptions are usually pretty quiet. They're non-explosive. You just kind of have lava like coming up onto the surface in a non-destructive manner. Our next type was the subduction boundary eruptions. Remember, subduction is when a plate converges and then sinks down because it's more dense. All right, this plate melts, becomes magma. These volcanoes are probably more like what you think about when you think about like a volcanic eruption. They're very explosive, very destructive. You're going to get that kind of classic like mountain-shaped volcano. All right, and then our last type of eruption are the hot spots, which are volcanoes that don't happen at plate boundaries. These are going to happen in the middle of plates at those hot spots. As the plate moves over it, it creates that line of volcanoes like Hawaii or Yellowstone. Okay, those different types of eruptions can make different types of volcanoes, and again, there were 3 of them. Our first one was a cinder cone, which is like a very short, steep mountain that's made out of cinders or ash from previous volcanic eruptions. So the volcano erupts, it's very explosive, all the ash falls back down and piles up. Our second type are the shield volcanoes, which are going to happen more at rifts. They're shields because they're large and they're dome-shaped, kind of like a shield. Very quiet eruptions, very non-explosive. Again, think Hawaii, even though Hawaii's at a hot spot. Still a shield volcano. And then our last type of volcano is what we think about when we think about volcanoes. If I were to ask you to draw a picture, you would probably draw this next type of volcano called a stratovolcano. And I like to think of a stratovolcano as a mix of both cinder cone and shield. So what happens is you'll have a very explosive eruption. These are at subduction boundaries. So you have a big explosion, big eruption. You'll have a layer of cinders fall down, a layer of cinders and ash, and then a quiet flow of lava. So what you end up with is alternating layers, cinders, ash, cinders, ash. All right, that builds up a very large mountain with very steep sides. So think like Mount Fuji, Mount Vesuvius, Mount St. Helens. Those volcanoes you probably already know. Most of those are strato. Okay? So what we're looking at today, we're going to look at the inside of the volcano. We're looking specifically at the magma and how the magma is going to change the eruption. You know, what makes an eruption more explosive? How come some volcanoes are like kaboom and then other ones are like bleep? Why? Why it be like that? Okay? So I'm going to full screen this bad boy. I'm going to jump back and forth betwixt the presentation and myself because I have some demos I want to show you with some fake magma. All right? So how does magma affect volcanic eruptions? So let's first define magma versus lava. What's the difference? And we talked about this in class yesterday. The difference is where they are. So magma is underground. Lava is on the surface. When magma gets to the surface, it becomes lava. And that's the only difference. It's not like they're made out of different things. It's just where they are. Okay? This magma down here is going to affect what kind of volcano you get up yonder. So let's look at how can magma be different from one another? How come some volcanoes, how can the magma of one volcano be different than another? It has to do with their compositions, what they're made out of, temperatures, and gas content. All right, we're going to focus mostly on the chemical compositions and the gas content, looking at how those are related. These factors impact how the magma behaves. Okay, this is going to affect what kind of explosion you get. Do you get a really big kaboom or do you not get a really big kaboom? Okay, so the first thing we're going to look at is silica. All right, silica comes from silica dioxide, which is found in crust. All right, as rocks melt and become magma, that silica is within them. All right. Different types of magma have different silica contents. I don't expect you to like memorize like the difference between like basaltic and andesite. These are like the three main groups of magma that I'm going to be referring to. But again, you don't necessarily need to memorize these. Okay, I just am showing them to you so you can see a relationship later on. Basaltic magma has a very low silica content. Andesite has a very medium silica content, whereas rhyolite has very high silica. Again, I don't need you to know the names. Just know that, okay? Basaltic is low, andesite medium, rhyolite high. Okay, cool. All right, so they can have different amounts of silica in it. All right, so what does that change? That changes the viscosity. I'll give you a moment to write that down because I need to go grab something out of my back room. Viscosity is the ability of a liquid to resist flowing. All right. So viscosity, if you think about different liquids, they have different abilities to either flow or resist flowing. Things that are thicker, like corn syrup, which I used to have, but for some reason I cannot locate it right now. That's okay. All right. Corn syrup has a very high viscosity. It doesn't want to move around. It just kind of stays in place, kind of like maple syrup. Baby oil or water has a very low viscosity. It moves around very easily, okay? So when we're talking about magma, let's look at this. Magma can have different viscosities. Basaltic magma has a low viscosity. It runs like water. Andesite magma is a medium viscosity. It's more like corn syrup. Rhyolite magma has a very high viscosity. It's super chunky. It's like peanut butter almost. You don't think about peanut butter as a liquid, okay? You don't think of it like a liquid usually, but it works in this case. All right, so I'm going to minimize that for a moment and bring it to me. So I want to show you how silica and viscosity go together. So what I've done, I have a container of dish soap. This is my magma. Pretend it's magma. Okay, it's not. If it doesn't have any silica in it, silica is basically sand. Okay, with no silica, it has a relatively low viscosity. It flows very easily. Okay, that's not too bad, right? That's not too bad. But if I were to add some silica or sand, silica is sand. I'm going to add just a bunch of sand in here. This is the life of a science teacher. We just mix stuff together. There's a reason, okay? And then I'm going to kind of incorporate all this. This is so delicious looking, right? And you're like, this is gross. All right, so this is a higher silica content. I've increased the silica because I've added it. All right, how did that change the viscosity? This is still a liquid, but it has a much higher viscosity. It does not want to flow as easily. It does not want to move, okay? So the higher the silica, the higher the viscosity. Remember that. The higher the silica, the higher the viscosity. I'm going to come back here. All right, that's really cool. So what else does that change? How does that make the eruptions different? Okay, so this one has more sand in it or silica. Why does that matter? This lava is thicker or more runny. How does that change it? Well, it affects the gas content. Magma has dissolved gases in it. Mostly water vapor, carbon dioxide, and sulfur dioxide. The water vapor can come from the ocean floor, where you have either subduction or usually subduction, generally the process that adds water vapor. Different magmas have different gas contents, and it goes back to their viscosity, okay? Remember, basaltic Basaltic magma has a low silica content, therefore it has a low viscosity. It's like dish soap, okay? If you were to take some dish soap and you put a straw into it and you tried to blow bubbles into it, the bubbles would escape very easily, okay? You can make a whole bunch of bubbles without trying a whole lot. You don't need a lot of pressure to build up, okay? Andesite and rhyolite have higher gas contents. That's because they have a higher viscosity, okay? If I go back to my example with my my high silica magma, my dish soap that I added sand to, if I try to blow a bubble into it, it's going to take a lot more effort, okay? Because the gases can't move around. They're stuck in that very chunky magma, all right? So what we end up with is a relationship, okay, between silica, viscosity, gas content, and explosiveness. If you have a higher silica content, that means the magma is a higher viscosity. High silica, high viscosity. If you have a high viscosity, the gases cannot escape. They'll be trapped, which means you have more pressure. Okay, if we have more pressure, think about pressure in like a soda bottle. Okay, if we add air into something, we increase the pressure. What's eventually going to happen? We get a bigger eruption. Okay, it's kind of like if you give a mouse a cookie. If you give a mouse a cookie, he'll ask for a glass of milk. Same thing here. Higher silica, higher viscosity. Higher viscosity, more gases, bigger kaboom. All right, and that's the moral of the story today. So, what I'd like you to do with this, okay, let's take a look-see. I don't think I added the transitions. No, I didn't here. That's okay. We can use this information, okay? We can look at volcanoes, looking at what we know about them, and we can figure out, okay, what's the silica content, okay? How explosive is this volcano going to be? Whatnot, okay? So I have a couple examples here. This one, Reventador. If I'm saying that incorrectly, I do apologize. This is in Ecuador in Central America. This volcano is on a convergent boundary. So we remember convergent, that's a subduction. Subduction boundary eruptions are explosive. Okay, well, why is it explosive? It must be explosive because it has a high viscosity magma. If it's high viscosity, it has higher silica. So I kind of worked backwards, all right? My next volcano I want to look at, it's kind of a snazzy one, it's called I don't know if this is Ale or Ale. I'm not 1,000% sure because it's a language I don't speak. Erta Ale lava lake in Danakil Depression in Ethiopia. And again, if I missaid any of that, I do apologize. I know that this volcano is along the East African Rift Valley. All right, well, what do I know about rift valleys? Rift valleys are rift eruptions, all right, at divergent boundaries. Those rift eruptions are non-explosive. Okay, well, if it's non-explosive, what can I tell about the magma? The magma is going to be runny. It has a low viscosity. If it's a low viscosity, that means it's a low silica. And after a little bit of research, which I did here, I found that this volcano is indeed a basaltic. Okay, remember basaltic is low silica, low viscosity. Shield volcano. Shield volcanoes are made from those non-explosive eruptions, all right? So all that information that I gathered over the last 2 days, I can use to describe this one volcano, okay? So what you're going to do now, you're going to take this information. You are going to continue to work on your volcano project, which is due tonight. You should be able to finish it. This was the last piece of information you needed.